So hi everyone, and welcome to my master thesis presentation. So for those who don't know me, my name is Mike Huisman, and today I'm going to talk about the research that I've done under supervision of Jan van Rijn and Aske Plaat. So let's get started. So the contents of this presentation are going to be the following. So first I will introduce you to the high-level problem that we're dealing with in this project. So afterwards we will see one potential solution, namely meta-learning. We will introduce our own meta-learning technique, which we call Turtle. Afterwards, we will do some experiments, discuss the results, and in the end, there will be time for questions and answers. Okay, so let's get started. So we are really part of an AI revolution at this point. We are seeing neural networks achieving great successes in various areas, from superhuman level image recognition performance to superhuman level game playing performance with AlphaGo, AlphaZero, Alpha whatever. And also we are seeing some great leaps in machine translation. However, there are some problems with these neural networks. And one problem of particular interest for our presentation is that they require lots of data. So this means that they are slow learners. Humans, on the other hand, are fast learners. So what we try to do is we try to bridge this gap between human intelligence and deep learning. And that means that we try to build neural networks that can learn from few data. And note that this is actually quite a different goal than what you're maybe used to in regular supervised learning, where you are given some task consisting of a training set and a test set, and your goal is really to optimize the predictive performance of your network. Now, this means that the end performance is really what is most important, and that the focus is not really on the process that leads to this performance. So the learning process itself is not deemed too important in this process. So this is what we are not going to do. So instead, we are really going to optimize the learning process of these networks such that they can learn from fewer data. But then the question, of course, is how can you actually measure the ability of these neural networks to learn new concepts quickly? And for that, you can kind of come up with the following description, and that is that given any task, we want our network to learn the associated concepts quickly. So note that there is this word any task in here, which means that we are not going to deal with a single data set, but really multiple data sets. So how this works is we present a task 1 to our model. It can learn on the training set. We evaluate how well it has learned on the test set, and we do this for some other tasks that we have. And what we have in the end is that these test set performances kind of indicate how well our network learns. But note that we are really interested in fast learning. And if our data sets become too large, then we're really not measuring fast learning. So for this reason, we make these data sets kind of small so that there are few examples to learn from. And then we enter the few shot learning setting. Okay, so now that we have this setting to really evaluate the ability of neural networks to learn from few data, it is time to look at some of the techniques to actually build neural networks that can learn in this setting. So for that, we're going to visit meta-learning, which is one approach to do this. And the key idea is to use previous learning experience to learn new tasks faster. So what this means, if our network is trying to learn task 2, we can leverage the learning that we have already done on task 1 in order to try to learn this task faster. And the similar for if we learn task M, then we try to learn use all of our previous learning experience on tasks 1, 2, and all the way through M-1 to learn this new task faster. So we're kind of looking for some kind of meta-knowledge that allows us to learn these new tasks faster. But then the question, of course, is, well, what kinds of meta-knowledge does allow you for faster learning? So there are many different forms that this can take on. So 3 examples of this are the neural network architecture that you can try to learn. You could try to find a good weight initialization. And also you could even try to learn the weight update rule. So in this presentation, we are really going to focus on these last 2 types of meta-knowledge. And more specifically, we're going to take a look at 2 popular techniques that try to do this. So the first one that we are going to take a look at is MAML, which tries to learn a good weight initialization. And the second technique that we're going to take a look at is the LSTM method, which not only tries to learn the initialization, but also tries to learn the weight update procedure, so the learning procedure itself. Okay, so let's start with MAML. So remember that the goal is really to achieve faster learning on new tasks. But there is one caveat here, and that is that regular learning is done using gradient descent. And gradient descent works as follows. If the x and y axis here correspond to parameters of your neural network, and the vertical axis, the z-axis, corresponds to the loss value that you're trying to minimize, then gradient descent simply tries to walk into the direction of the steepest descent to minimize this function. So then you may ask, well, if this learning procedure is fixed to be gradient descent, then how can we ever achieve faster learning on new tasks? So the key idea of MAML is here to learn a good weight initialization. So to learn good parameters to initialize your neural network, which allows for faster learning. And to understand this, we can take a look at a very simple example, namely this neural network, which maps a single input x and maps it onto our predictions y hat using two parameters. So we denote the parameters of the neural network using theta, and we can visualize this network in a 2D space. So on the horizontal axis, we have here the A parameter of the network, while on the vertical axis, we have the B parameter. And now the nice thing of this representation is that we can visualize tasks in this landscape. So these tasks we can represent by these blue dots, which correspond to the optimal parameters of our neural network that achieves the best performance on each of these tasks. So what MAML really tries to do is it tries to find some point in this 2D space from which you can learn these new tasks faster. And if you are human and you look at this picture, you may say, well, actually the center looks like a reasonable point, right? Because from the center you can move quickly towards each of these tasks, and this means that you can learn these new tasks quickly. And note that moving here really corresponds to applying gradient descent to each of these tasks. Okay, so this is really the key intuition behind MAML. But of course, in reality, we do not know all of these tasks up front, nor do we know their optimal parameters. So it's a bit more challenging, but what we do have is we have access to some tasks, and we also know our base learner architecture. And this is actually enough for MAML to find a good weight initialization theta from which we can quickly learn new tasks. So how this works is really by looking at what happens if you learn a single task. So suppose you are presented with a task J, and you apply gradient descent for, let's say, t steps. So what you get then is a set of updates. So your first update, your second update, until you have made t update steps. And then this represents your learned model. So we went from our weight initialization theta all the way to our learned model using gradient descent on this training set. Now, our goal is, however, to maximize the learning ability. And if you think about this, learning does not mean that you can memorize well, but that you can actually generalize well. So what we want is that if we have learned the concepts in this training set correctly, then we would also expect the performance on the test set to be reasonably good, right? So our goal is really to take this loss on the test set into account and to try to minimize this loss. And minimizing this test loss corresponds to maximizing our learning ability. And it turns out that is the beautiful thing of MAML, is that you can simply optimize this objective using regular gradient descent. So how this looks like is you start off with your random with your learned initialization parameters. You are presented with a task, let's say task 1, and then you make some updates on the training set. So in this case, we made 1, 2, 3 updates. Now we do the same thing for some other tasks that we encounter, and then we are going to evaluate the learned models, and we're going to evaluate how well they have learned on the test sets of these 3 tasks. Then we get these loss signals, and we can propagate this loss signal backwards through this computation graph, and that will give us this gradient signal right here, which tells us how the performance of these learned models here at the bottom depend on our chosen initial parameters. And if we feed this into gradient descent, it can simply propose an update for our initial parameters that presumably leads to faster learning of these tasks. Okay, so this is really what MAML tries to do. So we start off with a random initialization, And then we repeat this iterative process that you have seen on the last slide to kind of update your initialization. So we repeatedly sample these tasks and we update our initialization as you have seen on the previous slide. So how you can think of how MAML works is we start off with a kind of random initialization, and MAML tries to move this closer and closer towards the center, because from the center you can quickly learn each of these tasks. Okay, so an observation is here that MAML uses regular gradient descent to learn new tasks. So we learn a set of initial parameters, and once we are presented with a task, we learn this using regular gradient descent. A natural question that you may have, though, is there not something better than gradient descent? And that actually brings us to another technique, which is called the LSTM Method learner, which tries to replace this gradient descent procedure by a learnable procedure, by an LSTM network. So in this case, we will have two networks, namely our base learner network and a meta network. And this meta network is responsible for making updates to the parameters in this base learner network. So if you would compare their diagrams, all that has changed is really that we replace gradient descent by an LSTM module, by the separate meta network. And this network then tries to make updates to these parameters when presented with this new task. So how this LSTM module works is that if we are presented with a task J, we try to make some predictions on the training set. So we incur a loss value because of this, and we propagate this backwards in order to compute the gradients with respect to our parameters. So far so good, and this is also done by gradient descent. But what gradient descent would now do is simply apply a mathematical formula that tries to update these parameters using only the gradients. Now we are going to do something special, however, and that is that we are going to invoke this separate meta network. And we're going to try to use this meta network to make updates for our parameters A and B. So how this works is if we want to make an update for parameter B, we feed as input to this network the gradient of the loss and also the loss itself. And as output, we will get an updated weight B. We do the same thing for weight A, and in this way we have made one update step on the given task. Now you can of course repeat this procedure multiple times if you want to make multiple update steps on a task. And the cool thing now is that you can actually train this meta network to become better and better at making updates. So by doing this, you try to make it better than something like gradient descent. Okay, so now that we have seen these two techniques, my question really is, I'm not going to ask you because this is recorded, but which one would you expect to perform better? Is it MAML, which uses simple gradient descent to learn new tasks, or is it the LSTM Method learner, which replaces gradient descent by this LSTM module? And if you think about this for quite some time, maybe, or maybe not, if you're really smart, then you may see that the update step made by gradient descent is a simple linear function of the input gradient. So all that it does is multiply it by this learning rate alpha and move into the opposite direction, and therefore this minus term. And a property of neural networks is, well, even of a single neuron, is that they can approximate any linear function, right? So for this reason, you would certainly expect this LSTM module to be able to learn something as simple as this gradient descent update, right? And for this reason, you would expect the LSTM Method learner to perform either just as well as MAML, because it could try to learn gradient descent, or maybe it can even learn something better than gradient descent. Okay, so that was theory, and now we can take a look at some results that were presented by the authors of MAML, and they show actually that on image classification, MAML outperforms the LSTM Method learner. So that is very surprising, because in theory, the LSTM Method learner looks something like this, while in practice, it really looks something like this. So something strange is going on here, and that brings us to our new technique, which we propose, and that is called Turtle. So the driving hypothesis behind Turtle is really that it should be beneficial to learn a meta network to update the parameters of your base learner network. And if it is not beneficial, then at least you would expect to get similar performance than if you were just to use gradient descent. Then the question, of course, is still, then why was the LSTM method learner not as good as MAML? So for this, we formulated two hypotheses. Namely, the first one is that the LSTM model needs to learn how to maintain and interact with a state. And this introduces some parameters which may increase the complexity of the loss landscape that you're operating in. And in turn, this may make it more difficult to find a correct setting for this module. Another hypothesis comes from really understanding this computation graph, which you've seen before. So now it is for the LSTM method learner, but really it looks really the same. So the gray arrows are now not gradient descent, but the updates proposed by the LSTM module. And we no longer propagate the loss signals on the test sets backward to only the base learner network, but also to the meta network. So phi here represent the meta network parameters. Okay, so this backpropagation process of propagating this signal backwards along these red arrows is kind of expensive. So it requires you to compute second order gradients, which are quadratic in the number of base learner parameters. So to kind of sidestep this computational expense, the LSTM method learner makes a first order approximation. So naturally, you lose some sort of information because you're not really using the full second order gradients, but instead you're making an approximation, which is of course less complete and maybe contains some noise signals. So we think that this assumption may actually be hurtful. Okay, so we have formulated two hypotheses as to why the LSTM method learner failed to perform just as well as MAML. And we try to overcome these potential issues in our technique, which we call Turtle. So the first issue regarding the stateful nature of the LSTM, we try to resolve simply by replacing this LSTM module by a feed-forward neural network. And this feed-forward neural network does not have a state, and therefore has no issues regarding the state. The second issue is even simpler how we can solve this, and that is simply by not making a first order approximation, but simply by using the second order gradients. So yes, it is a bit more expensive, but maybe the performance is much better. So it's kind of a trade-off there. Okay, so let's dive into some experiments in which we try to investigate how well Turtle works compared to MAML and the LSTM method learner. So the first problem that we address is really that of sine wave regression, which was proposed by the authors of MAML. And every task here corresponds to a sine wave function. So here we have, for example, the sine wave function, and we are given access to some red dots, some training examples. So our training set consists of these red dots, and we also have a test set corresponding to these blue dots. And the goal of our base learner network is given an input coordinate, an x coordinate, to predict the corresponding y coordinate on the sine wave. So every training set will contain 5 examples. So this is not a lot. So this is very difficult to learn. And as a test set, we use 50 examples. So this is a bit larger to ensure proper evaluation of how it actually learned. Okay, so in total, we use 70,000 tasks to kind of determine the initialization parameters of this base learner network and also the parameters of this meta network. We use 1,000 tasks for validating, for doing hyperparameter selection, etc. And then 2,000 tasks to get this final performance estimate of how good our network is at learning. So we use the mean squared error as a performance measure. So after training on the training set, we measure the MSE on the test set, and that kind of indicates how well we have learned the sine wave function. Okay, so in total we perform 30 runs per algorithm, where every run consists of meta training, meta validation, and meta testing. And every run we start off with random initial parameters of both the base learner network and the meta network. So this kind of allows us to investigate the robustness to the random seed and random initializations. And we average the MSE over these tasks in these 3 stages to get a final performance estimate of these stages. Okay, so the base learner that we use is really the same as used by the authors of MAML. So it receives this single X coordinate. It is fed into 40 hidden nodes, followed by value activation functions. Again, 40 hidden nodes, followed by value activation functions, and then followed by our output prediction. So this is the Y coordinate that we think belongs to the input X coordinate. And what we use as a meta network for Turtle, we don't know yet, because Turtle is a new algorithm. So we really have to try out some different things. So this was really our first experiment where we did a grid search, which means that we tried out various combinations of hyperparameters. And I'm not going to really bore you with the results, but the outcome were really that the value activation function was performing quite decently, and also that we should only feed the raw gradient as input to this meta network. But a question that remained was, how about more hidden layers? And what about the order of information? So does it really matter whether you make this first order approximation or whether you use the full second order gradients? So here are the results. So this is if we make one update step per task. On the y-axis we have the mean squared error loss, and on the x-axis we have the algorithm. So either MAML or Turtle with different numbers of hidden layers in this meta network. And as you can see, for MAML, it really does not matter whether you make this first order approximation or use the second order variant. For Turtle, however, the difference between these first order approximations and the second order variant is very large. So this indicates that the first order approximation is really hurtful to performance. Now, a similar thing can be seen when we make 5 update steps per task. And that is that for MAML, it doesn't really matter whether you make this first order approximation or not. While for Turtle, the difference is really there, and the first order approximation seems to be very hurtful for performance. Now, if we make 10 update steps, we see something similar, but in addition, Turtle grows a bit unstable. Okay, so from all of these results together, we kind of see that 5 hidden layers in this meta network seem to give rise to best performance. So 5 to 6 hidden layers. We chose 5 for simplicity. And next, we really try to improve the stability of Turtle, because that seems to be an issue with larger numbers of updates per task. So we actually tried out 4 ideas to do this. So the first is to include a time step as input to this meta network, because this could allow it to learn kind of a learning rate schedule. The second idea is to include some sort of historical information. So even though this meta network is fully connected and has no state, we can still kind of put a state in there. It is kind of cheating by giving this as an additional input to this meta network. Thirdly, you may expect some issues with tunnel vision because the meta network and the base learning initialization were initially updated after seeing after a single task, while it may be better to update these parameters after seeing multiple tasks. And the last enhancement, which was quite important, is to learn a learning rate per base learning parameter. And if you combine all of these findings together, again, I'm not going to show you the full results, but if you put all of these findings together, then you really can expect to see something like this. So if we make one update step, Turtle is already decently good compared to MAML and the LSTM Method Learner, although the LSTM does achieve the best performance. For 5 update steps, it is already a bit more convincing, while for 10 update steps, we still really see the instability of Turtle. Okay, but these were not the full results, because if you include the last enhancement from the previous slide, namely learning a learning rate per parameter, you really see that Turtle is very convincingly outperforming all of the other tested techniques. Okay. So I have to be a bit critical here, and that is that we did hyperparameter experiments on these tasks that you see right now. So this picture is a bit too optimistic. So for that reason, we also did some experiments with image classification problems, for which we used two data sets. The first one being mini ImageNet, which is a small version of the large ImageNet. And the second is a COB, so a data set of bird images. And the task is really given an input X to correspond to predict the corresponding class of the image. So every task that we experiment with contains 5 classes, and either we use 1 example per class or 5 examples per class. So really this is still a very difficult scenario. Okay, so for meta training, to really find the initial parameters of this base learner network and to select the parameters of this meta network, we use 40,000 or 60,000 tasks, depending on how many examples there are per class. And both for meta validation and testing, we use 600 tasks. And we perform 5 runs with every algorithm, where of course every run is again consisting of meta training, meta validation, and meta testing. And we use the average accuracy across the task as kind of the performance estimate. So the base learner that we use is a convolutional neural network of 4 blocks, followed by a dense layer. Every block looks as follows. This is not too important right now. And as meta network, we do something special, and that is that we use the best found configuration on the sine wave regression problem. So whereas normally you would perform additional hyperparameter tuning on the problem that you are addressing, we do not do this. So we simply selected the best configuration of this meta network on sine wave regression, and now really apply this to image classification. Okay, so our meta network, as you have seen before, consists of 5 hidden layers with 20 nodes per hidden layer. And these are the results on mini ImageNet. So this is if you have 5 examples per task. This shows the accuracy, and the x-axis shows the algorithm. So the first 3 techniques are really transfer learning baselines, so they are not too important. This is the LSTM meta learner, which as you can see is very unstable as the performance is quite bad, and there is only this one outlier which is decentish but still outperformed by the transfer learning baselines. Looking at MAML and Turtle, we see that they're already much better than the LSTM meta learner, and we also see that Turtle seems to have a slight edge compared with MAML. So something similar can be seen when we have 25 examples per task. But now, in addition, the LSTM meta learner seems to be a bit more stable, although there is still this bad outlier. So looking again at MAML and Turtle, we see that Turtle sometimes again has a slight edge compared with MAML. Okay, so now we go to the next data set, so the COB birds images. And if we have 5 examples per task, we see something similar as seen before. Namely, the transfer learning techniques are outperformed by the meta learning techniques, while Turtle seems to have, again, a slight edge compared with MAML, and it is better than the LSTM method. Okay, this does not hold when there are 25 examples per task, so you cannot always win, because Turtle is here slightly better or worse than MAML, actually. But still better than the LSTM method. So yes, you cannot always win, but still Turtle seems to have an edge in many cases. So we did many more experiments, and unfortunately I cannot show you all of them today because of time constraints. So let's just discuss the results that we have seen so far. So a brief recap of what we have done is that we really hypothesized that it should be beneficial to learn this additional meta network on top of this base learner network that we have. But there was this surprising result in the literature, which shows that this was not the case for the LSTM meta learner. So for this, we formulated this new technique, which we call Turtle, and we found out that it often works. So both in sine wave regression, on 3 out of 4 image classification settings, and also in some settings where we transfer the meta network learned on tasks from one data set and transfer it to another data set. I haven't showed you these results today, but also there we found that Turtle works. So this really validates and confirms our hypothesis that it is often helpful to indeed learn the meta network that can make updates to your base learning network. Okay, some implications of this is that there is indeed a better learning route than gradient descent, which is in line with other findings by other researchers. And this learning route allows for better and faster learning. And as I have briefly talked about before, it also works in case of a task distribution shift. So if you train your base learner and meta network on tasks from one data set and completely just transfer it to another setting where you have tasks from another data set, we still found that Turtle works. So going from mini ImageNet to COB, we also found that Turtle outperformed MAML and the LSTM Method. Now, because this is such a challenging setting, this is kind of an open problem in meta learning right now. So we actually think that these learned optimizers are a very fruitful direction of future research because they really show some promise in this area. Okay, so going back to why the LSTM Method failed to perform just as well as MAML, we have now seen some results for Turtle, and we can try to kind of get an answer to this question. Well, it's not really an answer, but more just an hypothesis. And that is that for Turtle, we have seen that second order gradients are crucial for its performance. While the MetaLearner LSTM makes a first order assumption to sidestep the computation of these gradients. But if you think about this, if you make this first order approximation, it really makes your meta network unaware that updates that it makes at a given time step also influence the future inputs that it will receive at other time steps. So we think that this is very hurtful, and in future work you could try to remove this faulty assumption in order to improve the LSTM method. So we expect that if you would do this, you would get even better results than what we have so far with Turtle, because it has a more natural incorporation of stateful information. And just as a side note, we also think that the performance of Turtle can be improved if we were to perform additional hyperparameter tuning on these image classification problems that we have tested on. But for our purposes, we did not do this because we found that also without it, it was already better than the MAML and the LSTM Method in many cases. Okay. I have also to be a bit critical about Turtle, and that is, of course, while it is a bit better, it is also somewhat slow because we have to compute these second order gradients. So compared to other second order algorithms, of course, it is not much more expensive. We also tested and compared it with second order MAML, and it is really not much lower. So the cost is really dominated by this large base learner network that you have, and not so much by this small meta network. Even having that said, it is still really important to try to improve the speed of these algorithms because it is still quadratic in the number of base learner parameters, which can be quite infeasible and does not scale well to larger base learner networks. And if you try to improve upon this, maybe this is some work that you can take inspiration from.